Hi, everybody. This is Lawrence. I'm presenting today with Daniel, and we're really happy to see that we have a lot of participants already. We also know that developers sometimes, need to just finish this one thing. So we'll have a soft start and introduce the project. For those of you who haven't seen a lot about PX4 so far already. And we'd love to start with a halfway seriously meant statement, and that is, it's important as an open source project to get consistent quality. And Martin Golding has formulated the way to get consistent quality by imagining the maintainer, and the maintainer is the person who takes care of assembling all these different contributions into a whole, as a psychopath who knows where you live. Of course, that's not Daniel and me, but, or maybe it is. Daniel, what do you think?
Sometimes.
But generally, that is a very good way as a mental picture to think about how to develop software if you are in an open source community. My name is Zorens. I have created a number of open source projects with the first initial commits that are today really widely used in the drone industry. That's a Pixhawk hardware standard where I initially ran a small student team at ETH Zurich, Mavlink communication protocol, Q ground control, and PX4. And of course, I've just started them. There are hundreds of contributors, and this is not something where I really can take credit. But I have stayed with them for over 10 years now and consistently helped to find the right direction in this industry. And with that, I'd like to hand over to Daniel.
I'm Daniel Agar, a Canadian software developer that lives in Florida. I started contributing to these things, PX4, Q ground control, and Mavlink in about 2014. I focus on a lot of the core system architecture, development infrastructure, but I also like to dabble in all aspects of the system. And I worked on language runtimes at IBM in a previous life.
Yeah, and I'm convinced that Daniel is a way better developer than I am. So quickly for the call or for the webinar, housekeeping rules. The audience is all muted. We have over 100 people already on the call right now, so this would be unbearable. Please type your questions in the Q&A box at the bottom. We will run 2 polls that help us to understand how to run these webinars better. We will have time for questions at the end of the presentation. So we're going to start with the high-level picture, then drill down in a couple of topics, and then try to answer questions as we go. And the webinar is being recorded, and the content will be shared, so that if you need to leave earlier or if you want to show this to a colleague, you can. So quick overview of PX4. And before we dive into that, we would love to know what your role is. Are you more on the business side using PX4? Are you a developer? And that poll should be popping up now in front of you. So we'll leave 20, 30 seconds for all of you to vote. This really, really helps us to understand how we need to communicate what our development community, what the open source project is doing, and how to best disseminate what is happening here organically. Good. So what is already interesting and what I personally expected is we have lots of developers, but we have even more people who are deciding how PX4 is used in their products and services. And so I hope we will have high level information also for those today. Good. Then we want to quickly show the health of the ecosystem. So you can see that we have this nice, pretty much exponential growth of contributors in the community since 2011. And the fact that the last bar has many colors is actually one of the themes that will weave through today's call, and that is we have a real paradigm shift. Earlier, PX4 was really mostly a firmware for a microcontroller, but today it is a whole software stack, a whole software ecosystem of many, many different parts that together form an overall large piece of technology that's not just controlling motors on an airframe, but that is also using computer vision to detect and avoid obstacles. And that has really increased the load on Daniel and me quite a bit. So quite a paradigm shift that we experience every day. The next interesting thing to share is how PX4 is built. So there's commonly the misconception, for example, for Linux, that it is an operating system developed by nerds sitting in the basement in their underwear. And that is absolutely not true for Linux. There are, in fact, less than 10% non-professional full-time developers contributing to Linux today. And we haven't really done the statistics for this for PX4, but we have looked at how broad the distribution is. And we can see that the majority of contributors contributing to PX4 are working for many, many different companies, smaller companies, smaller individual contributors, which is good. That's really, really healthy. We don't want to have like, all the contributions coming from one direction. What you can see at the same time is that Auterion, the company that I helped co-found with Kevin, is already a really huge contributor. And that is because it's really aligned with the open source community and it's putting a lot of effort into the project and in many different directions. So you can see Auterion is contributing to pretty much the whole stack because it's distributing everything. And then also a great success story is Unique Research, which is the R&D division of Unique, which is a consumer and commercial drone manufacturer. And that is also really helping to advance the project. You can also see that Intel contributed, and number 5 is ETH Zurich. The companies identified by name here are the ones that are also members of the industry association, Drumcode. So that also means that the top 3 member organizations are on this chart. Overall, really healthy, really distributed, but at the same time, we have companies that have real commitment to the ecosystem. Which leads us to our next poll. Are you contributing to PX4 right now? So you can see the results of the poll right now. And what is awesome, and I think a big to do for Daniel and me, is that a lot of people are not contributing right now, but would love to get started. And it is our prime responsibility to support you on that. And if you have specific suggestions where you looked into contributions but failed, or where it's not clear where to start, please put that into the questions so we can address this on this webinar. Good. So we move on to the next poll slide. Good. Who builds PX4? We also wanted to use this slide to show you not all of the contributors. Those are the ones that showed up in the top 100 statistics of GitHub. And just to use this opportunity to say thank you to all the contributors, to everybody that helps us to advance this open source project, to show the diversity, and really appreciate for a moment how diverse and distributed the development is that is happening around the world here. And then what is also commonly a very confusing aspect, and we're starting to find better ways how to share that information, is like, what is this PX4 thing all around? And it is essentially built around one essential piece of technology, and that is the kernel, so to speak, pretty much equivalent to the Linux kernel. It is the core software that does the core flight control, but also core navigation for an autonomous robot that has the communication framework around it. And then within that, we have related projects like Q Ground Control, which is an app that allows you to control the drone, or the Drone Code SDK, which allows you to interface a drone. We have the Drone Code Industry Association, which is a Linux Foundation collaborative project, which helps to connect companies using PX4 with the development community. We have third-party projects that become more and more important in that ecosystem. For example, RAWS, that is an ecosystem we're interfacing very closely with. And then there are industry standards that we help develop, but that are used beyond just PX4. And those include PixHawk, which is the hardware reference standard, and Mavlink, the communication protocol. But at the end of the day, all of these efforts are circling around PX4 or are supporting it, like Drone Code. And overall, it's an integrated software ecosystem. So we have very different things. We have firmware on the vehicle, we have Mavlink, we have ROS 2, which we're using more and more. We have computer vision software. So it's a whole stack. And then it's used in many, many different projects and products. And that includes consumer and commercial vehicles from Unique. It includes a drone from Impossible Aerospace, many more, in going from consumer all the way to industrial. And a lot of these, most companies are contributing back and really helping us to advance this. And it's really awesome to see how diverse this is and how much traction it has in real products. Now, this graph is really important to grasp, in particular if you are coming to this webinar with a business background or a business role. What it shows is how these individual components develop over time. So you can see on the bottom left, it all starts in 2008 when I founded the PixHawk student team at ETH Zurich. And each of these components is growing very, very slowly over a decade. The problem is that as you do more and more with a drone, as you have more and more autonomy, as you can do not just manual flight, but you can fly missions, you need more and more software. And that software also keeps growing. And so you're accumulating technical depth. And as you add more and more pieces and all of them grow linear, of course, it ends up being a pretty much exponential function. And that forces us also within PX4, within the project, into a paradigm shift. It leads to a much broader vision, which is now focused around a whole software stack, which operates around a kernel, which is essentially the software piece that defines which interfaces you're using. And now the question is, great, okay, so this is getting more and more complex. The open source development community is providing that, but how does that influence my product or business? And so this is something that both Daniel and I have done a lot of times, helping companies to adopt this. So what is your usual experience, Daniel?
I mean, each of these slices represents a small, medium, or even large development team with full-time dedicated people. So if you want to build a product that touches all of these things, you can't possibly get the same depth. But they're all building blocks where you can take the 95% that you need and then add your special stuff on top.
And that is exactly what most of these companies are doing. They're adding the differentiation, and that's okay, because we want to collaborate in creating the base system. Like Linux is a base system for a web server. We're not collaborating to build all together a product, which is just not possible in the way this modern business works. But now the question is, okay, you've put that on top of the system at some point in the past. The red line shows today. Now, if you do it properly and you're not changing the underlying system, but you're contributing all the things that you need there in addition, what you can do is you can move up the technology curve in the future at a relatively marginal cost. And that is why open source is successful. It's an R&D model. It's a way how you can shift the non-differentiated load that technology creates into something that's shared and still differentiate. And I think what we will see is that companies that know how to do this will be successful in the next 18 months, and companies that just take the open source solution and run with it will struggle with this exponential growth.
Get left behind.
We've already talked about different use cases. So main thing for this slide, main takeaway message, consumer products need a reliable base. The open system is not so much a key aspect. For commercial, that's totally different. People, companies want an open system, want to innovate on top. And for industrial, our new way of having also PX4 software on the Linux computer is completely the one killer feature, of course, apart from safety and certification. Now we're coming to the meat of the presentation, which is the actual roadmap. And this is structured in having a very high level overview and then diving into a couple of key and some highlight topics. So what you see here is what we will do after the PX4 1.9 release. So it's not on the timeline here. Yeah, sorry. there's one marker incorrect here, but essentially these are the next things that we will work on after the release. Right now we have lockdown 1.9. We're targeting March. It's mostly in flight testing. And then the things to the right of this is the parallel ongoing development.
So should we just go through and call out a few of these things? On hardware testing, we're going to verify every contribution on every board we support upstream. We want everything to maintain a certain level of known support at all times. And if we can't do that, we're not going to support it. But that means a big rack of all the test hardware. The drivers overhaul, something I've been picking away at for a long time. We're going to have unified drivers across all platforms, SPI DMA IMU drivers, much faster. There's a new work queue framework for scheduling, full rate sampling, raw sensor logging. Maybe that's too much detail already, but you can tell what I'm excited about. We also have a lot of low-level improvements in the PX4 platform, micro orb improvements that save a lot of memory, real-time performance audit, eliminating all the remaining jitter in the system, and yeah, board and frame deprecation. If we aren't actively testing it, we're not going to have it upstream anymore. And let's see, fail-safe robustness tests are another good one. We're going to have automated testing in place to rigorously test all the fail-safes and make sure there are no regressions.
And go ahead.
Yeah, so avoidance, VIO, those are the bigger ones. We'll, I guess we'll come to that later on.
What's also important, you see an attribution to different persons and companies. What we have on the roadmap is not all the things that we will have in the next release after 1.9. This is essentially what we have committed contributions from different sides. So if you don't see something on there, but you would actually love to contribute it, there is no reason it should not get on here. But we've had in the past roadmaps that were more vision than a very concrete roadmap, and we've changed that to really focus on things where we know, where we've talked to individual developers, independent developers or companies, and where we know it will be delivered. And that is essential. And then the next release will happen September 2019. And for that, we have some of the larger work packages that we need to handle.
This one's a little bit more up in the air. Supporting D-Shot ESCs. We'll have feedback and logging from your speed controllers. That could be nice. The rate controller for multicopters, we're going to run that at least 1 kilohertz or as fast as you want. Another big one. Indoor navigation support. So again, back to VIO and some of the other things we'll touch on later, but you'll be able to do all of those same things, return to home, flying in a GPS denied environment, planning missions, that kind of thing.
Cool. And let's quickly dive into a couple highlight topics. So really from an architectural and capability perspective, biggest change is the introduction of computer vision, which really forced us to rethink how we do things. And the motivation is we need to be able to navigate if GPS is denied, if we're close to buildings, and we need to avoid obstacles because humans tend to get flight plans wrong. The number one reason for drone crashes is controlled flight into terrain or user error. And so that's really, really important. What we're doing there is to have obstacle avoidance using RGBD cameras or pure stereo cameras. main reason to not just use single point LiDAR or something along those lines is that we want to be able to detect and avoid also thin obstacles like a tree branch, like a cable, and be able to build on top of that later on for more complete navigation solutions. And that really requires a 3D understanding of the environment. In terms of algorithms, we are relying on simple baseline algorithms that are reliable. That is why I've chosen the vector field histogram approach, coupling it with an A star. So it's called VFH plus star. And that is something that has been in development as part of ETH research and work with students over the past 2 years, and is now getting developed by the development community into something that's really productized, really ready to use, really reliable, real time. And the way it works is, as you can see here, exploring different options at different time points and then avoiding the obstacle. We're running this successfully right now, mostly on Intel hardware, just for the sake of convenience, interfacing it with RealSense, which is a really decent, easy to use depth camera. But there is nothing in the architecture itself that would keep you from running it on anything else. We can run with a lot of cameras on an Intel NUC. We can run on a much smaller app board that's smaller than a Raspberry Pi. And we have a quick video. This will likely be choppy, but you can look at it on YouTube as well. We'll share that in the notes and a link to it. And essentially what you can see are two scenarios. One where the drone avoids an obstacle, which is a pretty simple obstacle. And then the next one is a more complex mission, a survey, which has been planned incorrectly. And also here, it can successfully avoid a tree, different type of obstacle. And this is really exciting because it's already built into the full autonomous mission flight. It's built into manual flight. And so we expect that more and more drones running PX4 will have that as a baseline feature that you just expect in the future, like you expect your parking sensors in a car today. Now I quickly...
Hello?
Good, next slide. So next step there in terms of roadmap, smoother trajectories. If you look at GitHub, that is already progressing really well. Support for lower compute platforms and using not just GPS, but also other feedback sources in terms of, sorry, not GPS, but other data sources in terms of potential obstacles. And that would allow us to track obstacles that are further apart. Good, that was the obstacle avoidance part, really exciting. Code is in a good shape. You can run it in CITL. You can contribute today. On vision, the other really important part is vision-based navigation. This is important if GPS is not available because you're indoors, because you have structures that obstruct the sky view, forests, interference, jamming. And this is a really important safety topic because without any positioning source, it's really hard to do a safe landing. And the ongoing work there is working with different open source software VIO pipelines that have been down selected from over 10 candidate pipelines that we've looked at. And that works with any camera source, essentially. And we're, of course, also always watching the market, and you might have seen the announcement from Intel for hardware tracking, for a hardware tracking module. And we have no special relationship with Intel with regards to that. So we're really excited to test any other hardware that becomes available.
Was that announced yesterday?
Yes. And I've seen 2 years ago a tech demo where it didn't look too bad already. So I'm quite excited to test this piece of hardware. The VIO pipeline is running on the chip itself. And we hope to see more like that. Good. If you have questions, we can try to answer a few on Vision right now. Otherwise, you find references below here to ask for more information. Cool. We had a couple questions about the role of RAWs. We will answer them in the next section because we're diving a bit deeper on that aspect. And that's where we come to system architecture. And the system architecture is really driven by the new things we're doing. And now that we have what we call the mission computer, which is part of the avionics package as a default component in most systems, we need to architect for that.
So big focus for me going forward is really reliability. How do we make this as robust as possible? You'll see a lot of new fail-safes showing up, contextual fail-safes, not just dumb thresholds, but different fail-safes for different situations. If you're a hybrid vehicle, a VTOL that takes off and lands as a multicopter, transitions to forward flight, there'll be different fail-safes in those different modes. If you are a plane flying out at a few hundred meters, you have different fail-safes than different requirements than when you're coming in for a landing. And we can handle all those situations differently and be a lot more reliable overall. Airspeed fault detection. If your pitot tube's plugged, there's a leak, something like that, we can use the estimator to flag that and fall back to a flight mode that doesn't use airspeed. For estimators, we're currently voting on sensors and we pass on the winning sensors to the estimator. We're going to flip that around and have kind of a matrix of estimators running on every sensor combination and then using the output of that to pick the winning estimation. And overhauled sensor pipeline, that goes back to the driver stuff I was talking about before, but there'll be a lot of changes there coming in soon. And this all comes back to making things as robust as possible.
So I think not to be underestimated is that we're really ripping the system apart right now in a good way. And because we have regular testing in place with CI, because we have the flight test team from Drone Code, we feel like we can actually do these things, and that was harder to do earlier. But there is always more we can do on the continuous integration side.
That's what makes a lot of these things tricky to do is to keep everything alive and working as we change it. I guess operating on a patient maybe is an analogy.
Indeed. There was a separate webinar we recorded a couple weeks ago about what the SDK is doing and how you can leverage it. This is something that we've really introduced as a major item this year. And in the backend, it's a C++ library, and that is what we're continuously building out. And then on the front end, you have different languages, language bindings, including Python, Swift, Java, and also Java for Android. And right now, we have a relatively small but focused and very successful developer group on the SDK. But this is something where if you ask us what is the roadmap for the SDK, it's really what you make the roadmap in terms of contributions. We'd love to see more companies contribute there. It's a much less obscure piece of software compared to the flight control system, where you need a very, very narrow skill set and very specialized skill set to be able to be successful. In terms of extending the SDK, adding language bindings, making it easier to use, adding installers, all the things that really make an SDK convenient and successful, that is general software engineering. That doesn't require working 10 years on drones and learning about all the secret sauce knowledge you need to have to evolve it. And so we hope for more engagement, more contributions there. And the way that SDK is architected, it will also lend itself to be run on board. So it's not just something to run on mobile or somewhere else. You can run it on board. You can run a Python script on board. You can control payload through it, and it's extensible by plugins. So this is something where we have quite a few commitments already from different developers. And we're also the two developers from Atarian, Julian and Jonas, are going to contribute heavily. But I'd love to see a lot more, and I think this is one of the most approachable ends of the system. Good. Now we come to the meat of the architectural change, and this is the 30,000-foot view. PX4 has always used a fairly modern publish-subscribe architecture to communicate between different, what we call a module, different modules, which is essentially one event loop, one thread, whatever language you're using naturally. And that allows you to build a standalone piece of software that executes logic. Now, another toolkit, which is written the same way, but which is not targeting microcontrollers or real-time controllers, but full-scale Linux systems, is ROS. And if you look at the PX4 API and the ROS API, they're not exactly the same, but architecturally, they're exactly the same. And we thought, well, we need Linux support, and we need to be able to bring more computer vision into this. And ROS already has a rich ecosystem. So why reinvent the wheel? And that is why we have created a seamless communication between UORB, which is essentially our publish subscribe broker, and ROS. And not just ROS, but actually directly targeting ROS 2. There's an adapter layer for ROS 1, so you can still use your existing nodes, but really the target is ROS 2. And that is native. So you don't have any translation ongoing. There's nothing that you need to write in terms of adapter code. You can directly talk from a PX4 node to a ROS node. And that makes it so powerful, because it takes a lot of the existing pain away that was present so far when you had to go through different things like Mavlink. So this is really, if you are an application developer and you're not just down in the system, this is a complete paradigm change. You now can build a hybrid system with PX4 where you can have first-class citizen nodes both on the embedded side as well as on the Linux side. And that allows you to benefit from the rich software ecosystem in Linux and in ROS, while maintaining safety critical functionality on the flight controller and keeping the flight controller software in itself mostly stable. And I think this is going to completely change how you develop software for drones. And that is also why we're targeting with our hardware reference platforms more and more integrated solutions that also have a Linux companion processor or some type of hybrid system architecture.
I guess to further confuse it, there are portions of PX4 that are ROS nodes. PX4 avoidance is running on ROS.
Yeah, we're becoming more and more a software ecosystem than really a code base. Cool. Then the other part is we also need to make it easier to work with the system.
So I'm not sure how many people on the call have actually done PX4 development, but it's a little difficult to get started. We've identified an IDE that lets us natively integrate with the actual PX4 build system, have all of your tools working in place, accessible from the GUI. You can click to select which board you want to build. You can click to run a simulation, click to debug that simulation running on your computer. You can even debug on hardware through this IDE. And it's just Microsoft VS Code with a certain configuration and a certain set of plugins. And we're going to make sure that the full developer experience works as close to perfect as we can get it. Okay, should I move on?
Yeah, I hope nobody minds that VS Code is developed by an open source team from Microsoft. You have to overcome your bias.
I think was it the most popular project on GitHub last year?
Yeah, I mean, this is awesome. I've stopped to explain people why open source is good and focus more on, on how we're making drones more safe, because that I think the baseline argument has been made successfully. So let's talk about a couple of system architecture questions. We will handle the safety questions in the next section because we have a couple more details on that. So we had a question on the SDK. Is the best way to connect Python or JavaScript on a website? We don't have, so we're using gRPC as the adapter layer for the SDK. So it wouldn't be too hard to build JavaScript bindings, and that would be a very welcome contribution. But we do not have JavaScript bindings right now out of the gate. And so I would say if you're a lot more efficient in JavaScript, please go ahead and contribute it. We've made it really easy to add language bindings. If you want to have something that is ready to go, then you can probably, your best shot will be Python, because that is something that is actively developed. But again, you will probably, if you have a JavaScript infrastructure, SDK is extensible, you can fix it yourself, you can extend it yourself, can make upstream contributions. You have all the control as a developer. I'm just reading more questions. What is the timeline to get a ROS2 integration as complete as a ROS1 plus MavROS solution? So that is an interesting question because there is a ROS integration in terms of integrating into the standard message set of ROS, which is quite successful with MavROS, and it's using the API of PX4 for that, which is good. That is kind of a different use case than if you connect a computer vision system, because on the computer vision system, you're not using PX4 with an API, you're kind of working inside of PX4. And so I would say MavROS does a really good job on the API level to send a set point or something like that. And that will stay some relevant value. It also isolates you from making mistakes yourself. what we're really targeting with the native ROS2 integration is that you can write a ROS node that's directly interacting with the flight controller, which is a more intimate relationship. And if you're looking for that, then it's ready today. Like nothing keeps you from starting to develop on that, and you will find it very pleasant if you do VIO or obstacle avoidance or anything like that, because you can directly communicate with the flight controller. So I think the answer is it depends. If you're really looking for just sending set points to the drone or even a mission or something like that, I think going through in the future through the SDK and going through something like Mavros or Mavros might stay your preferred approach, because it gives you an additional layer of isolation and safety.
But with that, it hurts performance because there's so many translation layers between
Yes.
microorbit PX4 to the Mavlink standard to Mavros, and finally to your ROS node. When we want to get past that with your ROS nodes talking directly to the modules in PX4.
Then a question is Mavros PX4 endorsed? Yes, lots of PX4 developers are using it. We even use it in our continuous integration suite, so we know it's working. We also have quite a few developers and contributors to Mavros in the PX4 community. Question also, which parts of the SDK are currently incomplete or work in progress? I think the core set is pretty complete and in good shape. I would say what is really incomplete are some of the language bindings that we have flagged. Like, for example, Java certainly needs love. And I think Python is in a good MVP shape, but certainly also probably could use more developers working on it. More questions. What does ROS give that isn't in other modules? That's mostly computer vision. So you need to understand that it's almost binary, whether you want to run something in ROS or if you want to run something very deep embedded on a microcontroller. Very rarely you will have something that is, you can run on both sides and it kind of makes sense for both. A real-time control algorithm for attitude control is something you want to run on a microcontroller because you get better performance. A computer vision algorithm or a complex navigation algorithm for obstacle avoidance is something you don't want to run on a microcontroller. It's something where you want to benefit from the additional libraries, the additional RAM, the additional compute available to you on Linux, while you're probably not as sensitive to real-time constraints there. So I would say higher level autonomy is what Linux and ROS give us in terms of navigation, in terms of perception, in terms of also connecting to other services like weather services or anything that is too heavyweight for the flight controller. And what is also beautiful, if you freeze the software on the flight controller, you can be a bit more agile on the Linux side without risking to break your reliability. And I think with that, we're moving on to the next section. Unfortunately, we won't have time for all the questions every time. So we saw there are quite a few questions about reliability and safety. Should we jump into that, Daniel?
Yes. Okay. There's a question about contingency management failsafe specifically for beyond visual line of sight flights. Return to home is not really an option for most beyond visual line of sight missions. What was the UTM work? Are you familiar with any of that, Lorenz?
Yes. So yeah. So we've kind of brushed over that. That is good that you raised this. I don't have a slide on this, but I can quickly talk through it. We have integrated the baseline functionality so you can upload a geofence to PX4. And then we've created an interface layer in ground control that allows you to connect to an airspace service with a standardized open source API. And the first adopter of that is AirMap. It's standardized, so we haven't hardwired AirMap into the open source software, but right now they're the only provider, and they have helped a lot to build this. So lots of contributions from AirMap on that front. And what it allows you to is to fly compliant with UTM in the airspace in the US and in Europe. You can register your flight, you can see where you have permission to fly, and you can download and upload geofence data from the nearest exclusion zones to PX4 to make sure that the system is not breaching the geofence or terminating the flight, even if it loses connection with the cloud service. And that's fully integrated, fully ready to go. It should be documented. And there's even UI support in ground control, so you can see where you're allowed to fly, and you can even file for permission to fly through the UI in QGC. So pretty natively integrated, state-of-the-art solution.
There's also been work on safe landing spots, or people call them rally points. It's an open PR and firmware. It can be revisited. It will probably be revisited at some point in the not too distant future.
Yeah, that is up in a PR. And what I would say is that there are multiple companies, including Otarian, working on BVLOS flight, and we have merged quite a bit of fail-safe functionality, automated termination of flights in the event of loss of control of the attitude, for example, which triggers a motor shutdown and parachute release. So this is all driven by ongoing discussions with regulators in the US and in Switzerland and across the globe. And we're watching very, very closely as an open source project what the real requirements are. So it's not just opinions or best guesses, it's real discussions with regulators to get permission to fly for special missions for BVLOS and other applications.
And we do have a variant of return to home that will fly back along your mission path and not just dart in a straight line. So there are options already.
So I would say overall, from a technology perspective, we're in a pretty good spot where I think we could definitely leverage contributions are from companies that want to solve that use case, that are willing to work with the upstream project, that do even basic things like flight testing these features and reporting bugs or reporting usability concerns they have. But it's the baseline technology is all there. And now it's about hardening it, putting it to the test, and making it easy to use. Great. Now we've talked about airspace integration, operational aspects. We're going beyond that. And one big disclaimer, we're not jumping to the conclusion that we need to fulfill a specific hardware standard yet or software certification standard, because the regulators are still looking into this. There's no drone standard as of now. But what we're doing is we're looking at safety standards from aerospace, from automotive, a bit more even at automotive because it has the right mindset and risk set and also price point. And we've done an initial failure mode analysis of PX4. We're collaborating with the functional safety lab at a university in Switzerland to continue that, not just at a failure mode analysis level, but even more in depth. And so they're running their statistical models. They're helping us understand how we need to implement those processes. And we have discussions on a drone code level with the FAA. And that all informs already heavily how we architect, how we do hardware reference designs. For example, the next hardware reference design will not just have redundant sensors, which we already have in many of the current designs, but also redundant power management. We're looking at automotive safety certified components, processors, even power management solutions. And so we're hardening the whole chain of things that go into PX4 already, oriented alongside of these standards, while the final verdict of the regulators, what is actually required for drones, is still out. And so if you're interested in safety, there are many ongoing things already, sprawling activity. Please reach out to me or to Daniel, and we can point you in the right direction. A lot of what we're doing is not really reflected in code because a lot has to do with understanding data, understanding standards, having meetings with regulators. And so you will see maybe like 5 or 10% what we're actually doing in that space. Good. So let's quickly move on to the Q&A section of that. We have a specific question about fail-safes for BVLOS. Yes, we're looking into that. We have merged changes. Well, I'm not sure if we merge it, but there is a PR up, a pull request, which enables exactly staged fail-safe management with an automated landing using a LiDAR to not crash into the ground, and also parachute controls for that. So yes, and that's all guided by SORA requirements. Then the next question is, can you please define the autonomy level of avoidance? I think we can loosely apply the autonomy levels that are applied for cars. I wouldn't go right now off the bat into an exact comparison because I would want to make sure it's an exact match. But what you can say is that we're not doing yet autonomous exploration or something like that. I've done that in my PhD times. We're still requiring an intent from the operator, be that a stick input for manual flight or a mission for autonomous flight. And then we try to stick to that user intent while making sure we're not crashing into an obstacle. So, for example, if you plan a mission through a tree, the vehicle will stay close to the mission as far as possible, but avoid the tree and resume the mission as soon as the obstacle is gone. That's kind of the autonomy level we have today. We don't have automatic planning, next best view planning for a survey in the system. And I'm not even sure if this is the job of the core flight controller or if this might not be actually something that is use case specific and should be implemented on a higher level. Then we have a question about how ArduPilot and PX4 compare. There's, of course, always the question, you know, what is more reliable? Some high-grade military autopilot, something from DJI, ArduPilot, Betaflight, PX4. I think that's really hard to do. I think what you can say about PX4 is that we're really focused on enterprise applications. That doesn't exclude consumer applications, as you see with some of the successful consumer drones in the market. But we are a full ecosystem driven by professional adopters, of course, by the developers of those. So I think that is the unique selling point, that we're trying to really be an awesome toolkit to build products from. Next question, are we going with automotive grade sensors? We go with automotive grade and redundant, both. And then any other safety standards we are considering? Yes, we've looked at pretty much everything under the sun. I've mentioned two very well-known ones, but at this point we're not trying to get carried away following any specific standards, but rather looking at the fundamental aspects of functional safety, which is understanding where risk is generated and then minimizing risk where feasible and where it's really easy and quick for us right now, while we work with regulators to understand what the formal requirements will be. And of course,
Right.
that discussion also informs them.
But I mean, the real standard doesn't exist yet. We can guess what it's going to be, but there's nothing really to point to.
But I think overall, more community contributions on that front would be great. I'd love to have more individual contributions on that front. I know that cargo drones are, for example, something that's really interesting to many companies. And I think safety is not a differentiator. Safety is just a given. And it would be great to see more contributions and interest on that front. Good. That is a great segue to upcoming hardware reference designs. I need to add a couple of disclaimers here. So first, we're an open source software project. The main reason we do hardware reference designs is that we find that a lot of the problems that we are confronted day to day are originating in hardware or are originating in differences between hardware that we're not aware of. And so we started off 2011-12 with an open source, open hardware approach, having a complete reference design out. I had the naive impression that this wasn't really too special or too important. And so this has been really successful, but 2-3 years later, I thought like, maybe other people are better than us at hardware. Let's just put out a pinout that they can follow, and then they know how to do hardware better than we do. Turns out that that didn't work well. It didn't work well for two reasons. One is we had deviations, and so different hardware would work in corner cases differently, which even led to some safety critical problems. And that was really hard to fix in software because we didn't know that the hardware we were running on was different, right? It looks all the same to the software that's flashed onto it. The second problem we were facing had really to do with capability, and that is the software developers also are exposed to a lot of product knowledge in the market, how people use it, what they connect to it, what's happening. And a lot of our hardware partners didn't have that knowledge. And so there were really wrong designs out that had made assumptions about what's connected to the autopilot that were incorrect. And so we're coming back now to a more holistic approach where we're trying to do hardware reference designs, not hardware products. And when I say we, it's really the community, so that we make it easier for people who want to build hardware for PX4 to comply to it, to have something that's reliable. And so let's look into that. We are currently at Flight Management Unit version 5, which is working great. We have multiple versions of that built out in the market. They go by the name of PX4. There's always an offset by 1, which is historic between the PixHawk developer hardware and the FMU version. And this is a TikTok design, like how I like to call that, like Intel does with its chip. So we do one big technology leap. That's a tick that was for us to upgrade to the STM32F7, which gave us about double the compute and RAM. And then now the talk is to optimize what a product manager would call product market fit. From a developer perspective, it's fixing all the things that, you know, we've learned. And so that is mostly about packaging, mostly about upgrading sensors. It's about power management. So it's not a completely new design from a processor perspective, but it's more industrial market focused, as we see a lot of people asking about safety, asking about if they can fly with heavier airframes. And so we want to harden the reference design for it.
And this year, you're going to see the firmware to evolve to really start to take advantage of these significantly improved compute performance, double precision floating point unit, the extra memory. We're going to use it.
And that also means, as a theme, you can expect the safety critical features to be only available on the F7 going forward. Like, we're not going to try to do everything on the F4. That it's unreasonable from a software development perspective to put that additional effort in when people anyway use new hardware. Another thing that we saw, there has been great innovation by different companies. And that is something I helped to create originally around 2014 back at 3DR when I worked as an open source developer with them, coming up with this initial cube design with a stackable solution, which is now in more and more vehicles, which is awesome. And this, at the same time, now that this is a need in the market, we need to standardize that. We need to standardize that so you have something like PCI for computers that is supported by multiple vendors, that you can rely on, that is informed by different directions. And that is a discussion I'm trying to spark here on the call, and that I would love to have with developers, with companies, with hardware vendors over the next couple of weeks. Do we already have a successful connector with what is out there? Or does the technology that has been created in the past couple of years actually force us to come up with a new standard? For example, having Ethernet on these pins. So my goal is to start that discussion, align on a roadmap, in a couple of weeks, then have something that we can narrow down as a PixHawk expansion connector, and then hopefully have companies wanting to build to that standard. So that is a very doable goal, but I think it's super enabling for the industry. And then, of course, we always have ambitions to even greater hardware. And those ambitions are around more compute, more RAM. We've seen that both ST and NXP have announced new designs. And yeah, that is something that is a little more out towards mid-end of this year. We know that different companies are already working on boards and hardware on that, but we want to make sure we, on the software front, do not just get distracted having more compute. We first actually want to make sure we have solid hardware in the market for these new use cases with heavier aircraft, and have the software infrastructure in place to leverage that.
But really, I think the F4, so STM32 F4, that's in all the PixHawks and PixHawk derivatives that everyone's familiar with, the jump from that to the F7 and the FMU V5 design is much bigger than the jump from F7 to these. So it'll be nice to have a little bit more compute, but it's not going to be, it's not going to unlock significantly more capabilities like F4 to F7 does.
Yeah, I totally agree. And something that is not on here, but that we've also started to look into, is safety critical processors. So you will see that we will bring Cortex R5 support to mainline PX4. Right now, I'm not super happy with the microcontroller market on that front. like the equivalent of an F7 or H7 is not available at an aggressive price point with those kind of cores. But that is something we also will look at, moving into a direction where we will have, in addition to our current reference designs, hardware reference designs, and that's an open invitation to chip manufacturers and board manufacturers that have all the functionality on board that would allow you to qualify this against ISO 26262. And we also totally expect that vendors will provide their own designs that are PX4 compatible and do that for the market. And so I think we'll have a mix of the general open source project moving into that direction and individual companies coming in with solutions that allow you to get a PX4 based platform hardware piece that is already safety critically certified or certifiable. I think.
Yeah.
Cool. So I hope that also answers most hardware questions. Yeah, I'm just looking at the questions, and I believe I've covered them already. If you have further follow-on questions, you can find me, you can find Daniel on Slack. The link is in the bottom right. Okay, we just got a new question. How can we contribute to the FMUV6 reference? That is a good question. There's a hardware channel in Slack. It's just hardware. Please join that. Then I think we will coordinate from there. And I'm going to make sure to keep everybody in the loop there.
It's a more general question about the roadmap. Going to make it public and want to be accountable that everything we claim is on the roadmap that we're actually going to follow through with. So we'll need to find a good place to keep that and keep it up to date at all times.
So most likely that will be a combination of the PX4 website and Discuss. Cool. I think we're pretty much through. That is the last slide. Thank you for joining. We hope that was useful to give you a high-level picture with some deep dives. And we will do this again and expect more webinars, in between on specific topics, most likely one on safety. Meanwhile, please make sure to use Discuss, to use Slack, to contact the core dev team. We're trying to be responsive as possible. Sometimes it's hard because we have so many users.
Yes, please let us know what you'd like to see.
Very cool. And with that, we're concluding. Thank you for joining, and we're going to make the material and the recording available.
Thank you, Lorenz.
Yeah, thanks, Daniel. And thanks for hanging out the last 4 years.